Okay, hello everyone. So today we will study Visual Language Action Models, in short VLA models. So we've learned imitation learning for last few lectures, and then so we will study how imitation learning and VLA models are connected, and then we will see some details of recent several VLA models. So let's start with the connection between imitation learning and VLA models. So over the last few lectures, we built up imitation learning. That is the philosophy of imitation learning is teaching an agent to act by mimicking expert demonstrations. And we covered 4 pillars in imitation learning, each fixing a weakness of the one before, starting with behavior cloning. The simplest approach, pure supervised learning on expert data, and Dagger fixes behavior cloning's distribution mismatch by querying the expert online, and Inverse RL recovers the expert hidden reward instead of copying actions, and the final one was Gale, matches expert behavior distribution within adversary objective. And so today we ask, what happens when we scale imitation learning up with internet pre-trained models? That leads to visual language action models, actually. So let's quickly recap behavior cloning. Behavior cloning treats imitation as plain supervised learning. Given a data set of expert state action pairs, we train a policy to output the expert's action at each state. That is the objective function of behavior cloning. It's simply just maximizing likelihood, right? This is exactly classification of regression. States are input, expert actions are labels. It is simple, stable, and needs no environment interaction, which is why it is default starting point. But the simplicity hides serious failure mode we saw in detail, covariance shift. Behavior cloning only ever sees states of expert visited. The moment the policy makes a small error, it lands in unfamiliar states. There it has no training signal, it errors more, drifting ever further from expert territory. So the below figure briefly shows the covariance shift problem. The blue one shows expert trajectory. These are seen during the training. Okay. So blue one is seen during the training, but it's starting with the small errors because of some reasons like sensor noise. Then learner drift into unseen states. Each mistake make next state less familiar, which make next mistake more likely. Errors compound. The y-error compound, the quadratic bound. Suppose the policy makes the mistake with probability at most epsilon on state it was trained on. Because each state pushes the agent into unfamiliar state where it may keep erroring, the cost add up over the period here. Total error, the upper bound is t squared epsilon. The total error grows as O t squared epsilon, quadratically in the horizon t, not linearly. The reason for the quadraticity is that there are large t time steps where a mistake can begin, and each mistake can cost up to large t further steps of drift. So the mathematical derivative was like yes, this one becomes this one, right? This quadratic blow-up is the single most important weakness of naive imitation, and every later method tries to tame it. How Dagger, inverse reinforcement learning, and Gale respond to that. Each method we study attacks the covariance shift problem from a different angle. Dagger collect data on the states that the learner actually visit ask the expert what to do there. So training and test state match. Inverse reinforcement learning, Do not copy actions. Infer the reward and the expert was optimizing, then playing with it, which generalizes better off distribution. Scale, train a discriminator to tell expert from learner and push the learner to fool it, matching whole behavior distributions. All three reduce drift, but they share one bigger limitation we have not yet challenged. The limitation they all share is that every method so far learns one policy for one task almost entirely from scratch. The robot's only knowledge of the world is whatever appears in its demonstration set, training set. If it is trained to pick up a red cup, it has no idea what a mug, a bottle, or the word blue means, because it never saw them. Collecting enough robot demonstrations to cover the whole world is impossibly expensive. Then what should we do? Contrast this with the human learner who already knows what objects are and what instructions mean before starting. The missing ingredient is broad, reusable knowledge of the world learned before the robot ever sees a demonstration. And here we have foundation model. Large language and visual language models solve a similar problem with now standard recipe. Pre-train on massive diverse internet data to observe general knowledge of language and images, then fine-tune or align on a smaller curated data set to induce the desired behavior. That is the standard recipe of today's large language or large visual language models. The pre-trained model already knows thousands of objects and the meaning of words, so fine-tuning needs far less task-specific data. The quick question for this lecture is, can we apply this same recipe to robot control? That is the motivation of visual language models. This is exactly the idea behind VLA models. Start from a pre-trained visual language model and teach it to act. And one useful trick for VLA models is action chunking. Before VLAs, one more idea is worth knowing because modern VLAs reuse it, predicting actions in chunks. Standard policies predict a single action per step. Action chunk predict a short sequence of future action at once. So what does it mean is that standard policy takes state as input, outputs action, and it goes to simulator. We have updated state, and that becomes another input here. So here only outputs a action of single time step. But instead of producing action in a single time step, action chunking predicts a short sequence of future actions at once. Here we have h length chunk, the number of future actions predicted together. The robot executes the whole chunk before predicting again, so it decides only once every h steps. The Y chunking helps. Committing to h actions shorten the effective decision horizon from large T to large T divided by h. Recall the error grew with the square horizon, this one, large O, T squared epsilon. So a shorter horizon directly shrink compounding error. This one, single time step, without action chunking. But action chunking, with action chunking, we only have to decide T divided by H times. Action chunking with transformers use this rich 80 to 90 success on delicate manipulation from only minutes of demonstration. Takeaway to carry forward is that most modern VLA models predict action chunks, not single actions. So we so far studied how imitation learning can be connected with VLAs, and then let's see VLAs in details. And let's start with the definition. What is a visual language action model? A VLA model is a foundation model for robot control. Its input is what a robot actually has: camera images of a scene, plus natural language instruction. Its output is robot action, for example, and the effector movement or joint commands. So here, visual signal and language signal becomes input of VLA, output action. So this is the reason why we call VLA model. So the policy now conditioned on rich perception and language, not a handcrafted low-dimensional state. Here, Originally, our policy function only takes a low-dimensional state, but now it takes a rich perception from image and language. Here, image and language. Currently, it is built on top of model already pre-trained on internet scale image text data. But this is the general formulation of VLA models, but these days, vision and language inputs are, of course, very important, but not enough, actually. I mean, these days, people trying to incorporate tactile information. Tactile information is like which you feel when you grasp something through your skin. I mean, without tactile information, making accurate contact with environment is greatly challenging. Imagine you're doing a virtual reality game. Imagine you're doing something in virtual reality without controller, with your bare hand. There's no glove, there's no controller. With your bare hand, you're trying to interact with some object in virtual reality with your headset. Then without haptic or force feedback to your hand, you cannot tell whether you successfully grab an object or not. Only based on visual inputs, you cannot say whether you really grasp that object or not, right? Because it is really ambiguous. When grasping some object, most of the object surface is occluded by hand. Hand is also occluded by itself, right? So there are many occlusions, and it's not. I mean, viewpoint is very limited. Egocentric viewpoint is very limited to check whether the grasp is successful or not. So that there are many ambiguities to check only with the image input. So that tactile information is very important. So that people these days try to incorporate tactile as additional input. Other than tactile, there are actually more inputs to VLAs, but let's see the basic formulation of VLA, just taking image and language as an action, output is action. The image, language are input, output is action. The anatomy of VLA. Almost every VLA shares the same 3 building blocks arranged as a pipeline. This is vision encoder, LLM backbone, and action head. Here, vision encoder converts the image into patch embeddings the model can reason over. The second one is LLM backbone, fuses image and language tokens and does the heavy reasoning inherited from pre-training. Last one is action head, turns the backbone's output into executable robot commands. Let's see each one in detail. So the first building block is a vision encoder. The vision encoder is the robot's eye. It maps raw camera pixels into sequence of embeddings. These encoders are themselves pre-trained on huge image datasets, so they already represent objects, textures, and spatial layout. Common choices combine complementary strengths. SIGLEAP is one of the widely used vision encoder, trained to align image with text, so its feature carries semantic meaning, knowing that something is a cup. Dynop V2. Several months ago, I think Dynop V3 has been presented, but Dynop V2 is still widely used one, trained with the self-supervised learning, so its feature captures fine spatial and geometric detail useful for precise control. Some VLAs fuse both SIGLEAP and Dynop V2, getting semantics and geometry at the same time. And second building block is language model backbone. The backbone is a large transformer, usually a pre-trained language or vision language model. It receives the image embedding and tokenized instruction and processes them together in one sequence. This is where the model's word knowledge lives: grammar, object names, relations, and common sense reasoning from pre-training. Because it's pre-trained, the robot inherits an understanding of language it never had to learn from demonstrations. Right? Likewise, vision encoder language model backbone is also pre-trained on large-scale internet scale data. Not only robot demonstration, but also there are many language and vision data sets, right? All such kind of internet scale data are used to pre-train vision encoder and language model backbone. The last building block is action head. The action head is where a language model becomes robot controller. Here lies the central design challenges of VLAs. A language model speaks in discrete tokens, but a robot moves in continuous space, joint angle, and position. What does this mean is that language are from like a dictionary, right? I mean, for example, I like an apple. Here we have, let's say we have a dictionary. This is dictionary, English dictionary. And I like an apple. Such kind of words are included in dictionary, right? And they are discrete, right? It's very hard to define something between I and like, right? It's very hard to define I and apple, right? But on continuous space, robot actions are continuous. We like to rotate a joint in a 30-degree or 40-degree or 60-degree. There are many numbers between 30 and 40 and 40 and 60, right? So this is continuous. So this is language. This is motion. Language is discretized. Motion is continuous. So we can reuse discretized structured output of language models, but robot is essentially continuous motion space. So we need to make a bridge discrete token and continuous motion, and that is the key choice that separates VLA families. Two dominant actions have emerged and they organize the rest of the lecture. So there are two ways to produce actions. The first one is discretized actions. Second one is continuous action. Discretized action, here, discretized action. A method that divides the continuous robot action range, for example, -1 to +1, into fixed interval and treats its bean as a distinct text token. For example, there are actually many numbers in between -1 and +1, like a -0.8, -0.5, 0.3, 0.7. There can be many numbers, right? But instead of considering all numbers between some floating point, we just make discretize them. For example, -1, -0.8, -0.6. There are like 20 classes, right? No, 10 classes, right? We can discretize floating numbers into 10 classes between -1 and +1. That is one way, right? Once we discretize floating numbers, then we can directly use LLM structure. Uses this existing language model structure and softmax layer directly without any changes. Easily models different choices left and right by giving separate probabilities to different action beans. But the problem is that it causes choppy movement due to rounding into fixed boxes and limit speed because tokens are generated one by one. But how about continuous action? It uses these floating numbers as it is. A method that directly outputs robot control commands as exact unquantized floating point continuous vectors. Outputs precise physical values, enabling fluid and fast real-time control needed for dexterous tasks. Generate the entire sequence of future action at once in a single forward pass, ensuring smooth and temporal flow. Standard regression cannot handle complex human behaviors requiring separate modules like diffusion flow matching heads. RT2 and Open VLA take the discrete route, this one. Pi0 rank route and 1 take the continuous route, this one. We look at each in turn. The first one, RT2, actions as another language presented in 2023. RT2 is from Google DeepMind, launched the VLA paradigm by treating robot control as text generation. It builds on large vision language models and co-fine-tunes them on web vision language task and robot demonstration together. Co-training is the trick. The model keeps practicing web question answering while it learns robot action, so it does not forget its word knowledge. I mean, literally, it trained together, trained the vision language and VLA together. The result is a single model that can both describe an image and command the robot. Each continuous action dimension, XYZ position, rotation, gripper, is split into 256 bins. Each bin is written as an integer, so full action becomes a short string of numbers predicted token by token. As I said, originally number actions are 7-dimensional continuous vector, but we discretize each floating point into 256 bins each, so that there are 7 discrete numbers, 7 action tokens. Because action are just token, the model's input-output format never changes, so web pre-training transfers directly. I mean, language models we can train language model with the web data, but they are just trained with a discrete text, right? But we can directly transfer such kind of language model to action models because they share the same representation. Payoff is RT2 shows emergent semantic generalization following instruction about object it never saw in any robot demo. Open VLA. RT2 was a closed model. It is not publicly available, so the community needs an open model with the same capabilities. Open VLA is that model. It is a 7 billion parameter VLA that anyone can download, run, and fine-tune. Like RT2, it predicts discretized action tokens decoded into 7D and the effector commands the robot executes. Its design makes a few deliberate choices that we unpack on the next slide. So this one first starts with division encoder. The fused encoder gives both meaning, siglip, align with the text, and find special detail, DynaV2, trained with self-supervised learning. It was trained on about 970,000 real robot trajectories from OpenX embodiment datasets spanning many tasks and robot bodies. Despite being 7 times smaller than RT2X, 55 billion, it beat it by 16.5% absolute success rate. It can be fine-tuned on a single consumer GPU using LoRa, putting VLAs with it within reach of ordinary labs. So far we studied RT2 and OpenVLA, but they, as I said, it outputs discrete action token, not continuous actions. So as I said, discretized action into 256 bins is convenient, but it has a real cost. The problem is coarse. Binning throws away precision, which are delicate tasks like inserting a plug or folding clothes. Right? I mean, in each bin, there can be many floating numbers, but all the floating numbers are treating the same action, so that the action space is very coarse, not dense. And slow, predicting actions 1 token at a time limits control frequency. So many real tasks need smooth, high frequency, high precision motion that token predictions struggle to deliver. This motivated a different action head. Keep actions continuous and generate them with a diffusion style model. And Pi0 is a continuous action, VLA, achieved with flow matching, presented in 2024. Pi0 from physical intelligence keeps action continuous instead of tokenizing them. It starts from pre-trained visual language model and attaches separate action expert. The action expert is trained with flow matching, a diffusion-like method that learns to turn random noise into clean action chunk through gradual denoise. You do not have to study flow matching, or you do not have to memorize what is flow matching, but you can think like flow matching is some algorithm for the diffusion modeling. It is more advanced version than DTPM, so these days people are widely using flow matching. It predicts a chunk of h equals to 50 future actions at once, enabling smooth control at up to 50 Hz, fast enough to fold boundary. You can visit Pi0 website and you can see that Pi0 robot, although it has a gripper with only 2 fingers or 3 fingers, like this kind of, this kind of finger, it do some kind of laundry folding. Instead of predicting action tokens, the action expert learns the denoising process, as I said. Start with random noise, flow matching, denoise it to make it clean action chunk. Starting from a noise, the model takes several steps to arrive at a smooth, valid action chunk. This produces continuous high-frequency motion and naturally represents many equally good ways to move. Follow up Pi0 Fast as a fast token variant and Pi 0.5 improves open word generalization. Same pre-trained brain as RT2 and OpenVLA, but the generative continuous action had instead of discrete tokens. And NVIDIA Groot N1, a foundation model for humanoid, presented in last year, 2025, very recent, right? Groot N1 is an open foundation model aimed at generalist humanoid robots. Its defining feature is a dual system design, inspired by theories of fast and slow human cognition. It is trained on heterogeneous mixture of real robot trajectories, human videos, large amount of synthetic data. This data strategy tackles the central bottleneck of robots. Real robot data is scarce and expensive. NVIDIA generated 100,000 synthetic trajectories to supplement limited real data. I mean, before this kind of robot model, NVIDIA actually was very good at generative modeling, starting with they presented many GAN papers, I mean, in 2019 or 2020, and they also have lots of good diffusion model research results, so that such kind of thing, and also combined with the Unreal Engine, or they are some computer graphics based data, they can synthesize many high quality data that can be used to train robot models. So Groot N1, a dual system architecture, there are two systems. System 2, think, it interprets what it sees and what it is told and decide what to do. It's like vision language reasoning, right? The vision language part in the VLA model. And then system 1 is now an action part. It generates fluid real-time motor command using a diffusion transformer. The two systems are tightly coupled and trained jointly end-to-end, so reasoning and acting improve together. Embodiment-specific encoder map each robot's unique joint into a shared space, so one model controls many bodies. Let's compare them. We learned 4 VLA models: RT2, OpenVLA, Pi0, and Groot N1. You do not have to memorize backbones, but action representation. They are discrete, continuous. It is also continuous. The trend is clear, actually. It moved to continuous, right? Early VLAs reused LLMs by tokenizing actions. Newer ones add a continuous generative head for smoother, more dexterous control. It's, obvious, clear. And let's see how VLAs are trained. At heart, VLAs are still trained by imitation, maximizing likelihood of expert action given the observation. For token-based model like RT2 and OpenVLA, this is ordinary next token prediction over action tokens, just maximizing likelihood. Here O bundles the camera image and language instruction, and A is the possibly chunked action. It is same cross entropy laws used to train language model just over action tokens instead of words. But for continuous models, as I said, we introduced diffusion and flow matching. Action head is trained with the denoising objective instead. The model is given noised action chunk and then learns to predict the denoising direction that cleans it up. Intuitively, the model learns the flow that turns noise into clean action chunk. Different laws, same spirit. Both objectives simply teach the model to reproduce the expert. Both means the loss function of the discrete model as well, discretized model as well. For the discretized, like RT2 and OpenVLA, and continuous model like a Pi0 and Groot, all of them, both objectives, simply teach the model to reproduce the expert. So that we can say essentially it's behavior cloning, but pre-trained on internet scale data. Both are built on top of internet scale pre-training, which is what gives related generalization. So the big picture is scaled up imitation. Step back and notice what VLAs really are. Imitation learning, basically it is imitation learning, but scaled up with foundation model brain. The learning signal is still copy expert exactly as in behavior cloning. What changes is the starting point. Instead of blank, randomly initialized neural network, we begin from a model that already understands images and language. That pre-trained knowledge is what lets a VLA generalize to new objects and instruction far beyond its robot demonstrations. This is the payoff we were chasing at the start, escaping from scratch imitation of classical IL. So it turns out that loss function is almost the same as the imitation learning, but the major difference is starting point is as the starting point. We start from the pre-trained model, which understand the word, image, language, understand the word. Of course, there are limitations. VLAs inherit imitation learning's fundamental ceiling. They can only be as good as their demonstrations. Imitation has no notion of better or worse. It only copies, so it cannot serve as demonstrator. They struggle with long horizon tasks that require chaining many steps together. They handle rare or novel situations poorly when those are absent from the training data. They have no built-in way to recover gracefully from their own mistakes. To push past these limits, we need a signal of what is good, not just what the expert did, right? So, share the same limitation, covariance shift. Although we have starting point is different and we have huge scale data set, covariance shift still remain. And the signal of what is good is exactly what reinforcement learning provides through reward and preferences, right? The plan for the rest of the course closes the loop from imitation back to reinforcement learning. So this is quite interesting point. We've learned like many RL algorithms like a DQN, policy gradient, PPO. Those are RL algorithms. They do not have explicit target. We need to optimize indirectly with PPO. How about imitation learning? behavior cloning, Dagger, VLAs. They are based on imitation learning. So VLAs is scaled up with the scaled up pre-training. It achieves some kind of generalization in open world environment, but it still suffers from covariance shift, so that now people are trying to going back to reinforcement learning. So that the good point of imitation, VLA model is that we can, with the supervised learning, basically IA is supervised learning. Supervised learning, at the beginning of the training, the network is quite fragile and unstable, so that strong signal from supervised learning is very beneficial. But once we reach to some point, the performance is still suboptimal. Then we revisit reinforcement learning. Next lecture. That is next lecture. DPO, GRPO, two modern ways to align model directly from preference and reward. That is very recent research topic. Post-training. Once we train diffusion, it's not only about VLA models. It's also applicable to video generative models. Once we train video generative models or VLA models with supervised learning, diffusion learning or anything, those are supervised learning, right? Supervised learning, but performance is still suboptimal. Then what should we do? Then we are going to revisit reinforcement learning to say like explicit preference, reward. That once we train with this supervised learning, we go to reinforcement learning to do post-training. This is very interesting point, I think, right? For example, when we finish training video generative model, but the generative video is physically implausible, how should we do? One way, of course, is, increasing data, enlarging data, but these days people try to revisit RL, DPO or GRPO to make it better. So after they applying this method to fine-tune VLA models, that is called post-training. Post-training. So they improve beyond their demonstrations. The story so far, imitation taught the robot to copy. Reinforcement learning will teach it to improve. So that they are, although this lecture's name is reinforcement learning, IL also is very important, and combining them together is very recent research topic. So let's summarize. Classical imitation learning train narrow from scratch policies and suffer from compounding error. Action chunking shortens the effective horizon and is reused widely in modern models. VLA models apply the foundation model recipe to robotics, pre-train on internet data, then fine-tune to act token-based VLAs like RT2 and Open VLA. Reuse the LLM, continuous VLAs, Pi0 and Groot, add a diffusion-style action head. At heart, VLAs are scaled-up imitation. Passing their ceiling is the